Hello. Last week we were talking about independent samples, which was all of what Chapter 9 was about. And so now we're going to talk about a related samples t-test, and that's what all of Chapter 10 is about. A lot of what we're doing in this chapter is a repeat of what Chapter 9 was like, which was a repeat of what Chapter 8 and 7 are like. Remember how I said that hypothesis testing just becomes a repetitive task. You're just making some minor changes depending upon how many samples you have, the kind of data you have, and some minor tweaks to the statistic. Again, so research designs change, the statistic changes a little bit, but all of the steps pretty much stay the same. So a related samples design is where samples are not independent of each other. They are actually related in some way, that who's getting into one sample does affect who gets into another sample, and so there is a relationship there. So once participants have agreed to be in a study, their assignment to the different levels of the independent variable are not random. The people who are in one group do affect who gets in the other group. There are two major ways to make related samples, and then within each one of those major ways, there are two ways. So we're actually talking about 4 different research designs, and all of those are related samples. So let's first look at the repeated measures design. One way of doing a repeated measures design is called a pre-post design. And I'm going to use a clinical example as an explanation. So let's say we have a bunch of people who have spider phobia, and we want to see how effective a behavioral treatment is for that spider phobia. So we're going to ask patients before they undergo that treatment to take a test to measure their level of phobia prior to any kind of treatment. So that would be a pre-treatment test or pre-test. So here's their pre-test levels of phobia. Then we're going to give all of those same people the treatment, the behavioral treatment that we think might have an effect. And then we measure their levels again after the treatment or post-treatment, which is called a post-test. These are all the same people that are pre-post. So we still have the same idea that we have an independent variable that we're measuring, and there are 2 levels. One is prior to any treatment, so it would be a 0 level, and then let's say we gave them 6 weeks or 6 sessions of the behavioral treatment. So that would be the other level of the independent variable. And then the dependent variable is their level of phobia, and we want to know, does treatment affect their level of phobia? So that would be a pre-post design within the repeated measures approach. Another way of doing a repeated measures design is called a within subjects design. Here, instead of looking at pre-treatment and post-treatment, we're actually going to compare 2 different treatments. We're going to give them 2 different levels of the independent variable and see how it affects a dependent variable. So here we're looking at exercise, and we want to know, does aerobic exercise improve memory for material after they've done the exercise, or does anaerobic exercise affect their memory? So rather than a pre and a post in terms of a treatment, we have 2 different treatments. Exercise, type of exercise, is the independent variable, and memory is the dependent variable. It is again a repeated measures design because it is the same people, and they are just getting 2 different conditions of the independent variable. So here we have their memory scores from one condition, their memory scores from the other condition. It's still the same 4 people. That's what makes it a repeated measures design. We are repeatedly measuring the same people. So again, so why it's called a within subjects is because the change is within the same people. We've changed their ability to remember something by giving them different conditions of the independent variable. Another way of creating related samples, and here too there are 2 strategies for this, is called a matched pairs design. The first one we're going to talk about is the experimental manipulation to make matched pairs. So in this design, we do use 2 different groups of people. However, we are going to see in what way they are related. Okay, so for this experiment, we are going to measure some characteristic that we think is going to affect our outcome. And then we're going to match people on that characteristic. And then one person in that pair is going to go into one group, and the other person who has the same level of that characteristic is going to go into the other group. Okay? So you'll see how that's why those groups are related. Because the one person in the pair went to one group, that person's partner is going to go into the other group. Okay? What this does when you match them this way is that it assures that those two groups are the same on this characteristic, so that it doesn't affect the dependent variable at all. So to give you an example, let's say that we are looking to create, we're actually looking to test a training program that improves the free throw ability of basketball players. Okay, so what we're doing is testing the effectiveness of the training. Right? So training program is the independent variable. How well they're able to shoot those kind of baskets is the dependent variable. But we do know that height affects a person's ability to successfully throw a free shot. So what we basically do is going to measure the heights of all of our participants and then match them on height. We're going to say, okay, here's one person who is a certain height, 5'9", and another person who is a certain height, that same height, 5'9". We're going to put one of those people that's 5'9" in the no training group and that person's partner or that matched pair in the other group, the training group. So you'll see that you have a 5'9" in the training and a 5'9" in the no training, a 6'1" in the no training, a 6'1" in the training, a 6'2" in the training, a 6'2" in the no training, and so on. So that height is not different between those groups. The only thing that's different between those groups is that one got the training and one didn't. So you're matching them on a variable that affects the outcome of your study. Another way of doing a matched pairs design is called natural occurrence, and these are when your pairs are already naturally matched on something. So probably the most common natural occurrence matched pairs design is when people are literally related to each other, like identical twins. So for example, we gather a bunch of identical twins. We were trying to see how effective the level of medication that you give somebody who has a mood disorder. And we do know that genetics affects the severity of the mood disorder and how medication might interact with them. So we've got identical twins, both of whom suffer from a mood disorder. One twin's going to get the 20 milligram dose. That person's identical twin is going to get the 50 milligram dose. So those two groups are exactly the same genetically. So when their mood disorders look different at the end of the study, it can't be because of different genetics. It has to be because of the dosage or chance. Okay. So repeated measures and matched pairs. The related samples design is a much more appealing research design. We do like that design. Why? Because they are more powerful. They are more powerful than the independence samples design, and here's why. And your book goes into quite a bit of detail on this explanation. It's on page 265. But overall, what it does, it reduces the standard error. Okay? When you look at independent samples designs, independent samples have multiple sources of error. Between persons, which can be due to individual differences and the independent variable, and within groups, which would just be due to individual differences. In a related samples design, you are eliminating the between persons, the individual differences problem, because it's all the same people, or they're at least matched on something that's going to affect the outcome of your study. So in the be-all, end-all, related samples do have more power. They reduce the error term. The error always goes in the bottom of your statistic, and if you have a smaller number in the bottom, then you're going to get a larger outcome when you do the division. So we're always going to get greater obtained values for that reason. We also like this design because when you think about it from a research design point of view, it does reduce or even eliminate rival explanations as to why the groups are different. Okay, so if we take the example of the people getting treatment, we've measured those people prior to them getting treatment, and then we gave them all the treatment, and we measured those exact same people after getting the treatment. So if they change in some huge way, then here's the only explanations for why we could have gotten that change. One was the treatment. What happened between the time we tested them the first time and the time we tested them the second time? It was the treatment. But time also was passing. If we gave them, what did I say, 6 treatments, that would be 6 weeks. We do know that for a lot of mental disorders, just the passage of time might reduce the problem. So that's a possible rival hypothesis. But everything else has been, age, race, anything like that, it can't be any of those because they're the same people. And then we also have chance, because we always have chance. But our research, our statistical calculation is going to tell us how much chance is operating. Okay. So if you had independent samples and one of those groups got the treatment and the other one didn't, there are all kinds of reasons why that second group who got the treatment might be different other than the treatment. It could be all the other characteristics about those groups that make them different. Maybe that group had worse levels of phobia, and you don't know that because they're different people. In the related samples, you do know that. You measured them all before you gave them treatment, and then you measured them all again after treatment. So it does eliminate a lot of the other explanations. So that's another reason why we like this design so much. However, when you do this, you do cut the sample size in half, and that reduces power. So you have to make sure that you do have enough people in the sample, because when you go to do the statistic, you're going to be cutting it in half and thus reducing power again. Okay. So the example that we're going to walk through is the one in the textbook. We're going to look at reading, the amount of time spent reading when a teacher is in the room and when the teacher leaves the room. They had 8 kids, and they measured them at 2 times, which if those samples were independent would be an N of 16, but now we only have an N of 8. Okay. So let's look at how we're going to calculate this T statistic. Okay. We're basically computing an average difference between these 2 samples, pre-post or matched in some way, okay, to an average difference that we would expect if there was no effect of the independent variable on the dependent variable, which is basically a 0 difference. We're looking at the average difference we got compared to a 0 difference. Remember, 0 is always in the null, and it's always the null that we're testing. So we have to compute all of our differences between our pairs of scores, and remember the example that I'm using is the teacher being present versus the teacher being absent, and that's why I like those subscripts, because they tell you exactly what it is you're computing. And then we're going to make an average of all those differences by adding up all the differences we've just computed and dividing by the number of differences we have. So the differences added up to 120. We had 8 differences. Our average difference is 15 seconds. Okay, so that was the average difference in length of time reading from when the teacher was present to when the teacher was absent. Okay. We're going to designate that average difference capital M with a subscript of a D. So that's telling us that's a mean difference, okay, or an average difference. We're going to compare that difference of 15 to a difference of 0, which is what we would expect if the status of the teacher, whether she was present or absent, had no effect on reading level. Is that 15 significantly different from a difference of 0? That's our question. Okay. So let's look at how we calculate the T. It's a ratio. It doesn't look any different than the T's that we have been calculating. There's our value that we got from our experiment compared to the value in the null over a standard error of the mean difference. Standard error of the mean difference is a standard deviation of a sampling distribution of mean differences around an average of 0. Just like all sampling distributions, they are constructed as if the null were true. And so the null says that the average you get is going to be 0. They're all going to be normally distributed around that. And then you can compute a standard deviation of those mean differences. And that's what a sampling error of the mean difference is. So we go ahead and we calculate the statistic, and I'll do that in part 2.